In many cases, we want to know if a function is continuous over a region and then integrate to find the area under the curve. Integrands should be checked for continuity over the integration range. Sometimes we run into scenarios where a function is not continuous at one particular point. If a discontinuity is found, then the range of the original integral should be broken into two pieces. We would add together the integral of f of x evaluated from the lower limit to the point of discontinuity and the integral of f of x evaluated from the point of discontinuity to the upper limit. This gives us the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. We can evaluate these integrals using limits because the function is discontinuous at the point c. So we have the integral from a to c of f of x dx is equal to the limit as t approaches c from the left of the integral from a to t of f of x dx, and we have the integral from c to b of f of x dx is equal to the limit as t approaches c from the right of the integral from t to b of f of x dx. If both limits exist, then both integrals can be evaluated, and the result is equal to the original integral. Let's work through an example of this. Here we want to evaluate the integral from 0 to 2 of 4 over x squared plus 2x minus 3 dx. Since there is a variable in the denominator, we are likely to have a value of x that makes the denominator 0, which would be a discontinuity. By setting the equation in the denominator equal to 0, we can observe that there is a discontinuity at x equals 1. This means we need to break the integral into two regions. The first region is 0 to 1, where 0 is included but 1 is not. The second region is 1 to 2, where 1 is not included but 2 is. To perform the integration, we need to use partial fractions to rewrite the integrand. We have our original integrand, which is 4 over x squared plus 2x minus 3, and we'll set that equal to a over x plus 3 plus b over x minus 1. We get these denominators from factoring the polynomial. Multiply both sides by the left side denominator, which yields 4 equals a times x minus 1 plus b times x plus 3. The x terms must add to 0, and the constant terms must add to 4, which yields a equals minus 1 and b equals 1. Finally, we have 4 over x squared plus 2x minus 3 equals 1 over x minus 1 minus 1 over x plus 3. Written this way, the discontinuity is obvious. Finally, we will integrate by employing the partial fractions and breaking up the integral. So we have the integral from 0 to 2 of 4 over x squared plus 2x minus 3 dx equals the limit as t approaches 1 from the left of the integral from 0 to t of 1 over x minus 1 plus the limit as t approaches 1 from the right of the integral from t to 2 of 1 over x minus 1 dx minus the integral from 0 to 2 of 1 over x plus 3 dx. The integration yields natural logs for each individual integral. This gives us the limit as t approaches 1 from the left of the natural log of the absolute value of x minus 1 evaluated from 0 to t plus the limit as t approaches 1 from the right of natural log of the absolute value of x minus 1 evaluated from t to 2 minus the natural log of absolute value of x plus 3 evaluated from 0 to 2. Recall that the natural log of 1 is 0. Therefore, we have the limit as t approaches 1 from the left of natural log of the absolute value of t minus 1 minus the limit as t approaches 1 from the right of natural log of the absolute value of t minus 1 minus natural log of 5 minus natural log of 3. We can see that the first limit goes to negative infinity and the second limit goes to positive infinity, so the result is negative infinity minus the natural log of 15. We would consider this to be negative infinity. Therefore, the integral diverges.